Welcome to Sleepy Construction. Close your eyes and let's build. Tonight, we are going somewhere different. Not a desert, not a city, somewhere with no ground at all. 250 miles above the surface of the Earth, in the near total silence of orbit, where nothing has any weight, and every single piece of what we're about to build had to arrive exactly the way it left. Because there was no factory up there, no crane, no solid ground to stand on while you worked. Tonight, we build the International Space Station. Slowly, module by module, bolt by bolt, just the way they did, 500 kilometers above everything you have ever stood on. If you'd like to keep building with us, night after night, a like and a subscribe helps this small channel grow. And if there's a structure you've always wondered about, tell me in the comments. We may just build it together next. You don't need to remember any of this. You don't need to follow every detail. You can simply let the story carry you quietly. The way the station itself now drifts quietly above the Earth, circling once every 90 minutes, forever falling and never landing. So settle in, get comfortable, and let's begin. To understand why the International Space Station exists at all, we need to go back a little further than its actual construction. We need to go back to a rivalry. Through the 1970s and 1980s, the United States and the Soviet Union were locked in a long, tense competition for dominance in space. A competition that had already produced satellites, moon landings, and increasingly ambitious space stations, each side quietly trying to outlast and outperform the other. The Soviet Union built a series of space stations under the Salyut program. Then, in 1986, launched Mir, a station that would eventually remain in orbit for 15 years, hosting cosmonauts for record-breaking stays, proving that human beings could live and work in space for extended periods, not just visit briefly. Mir itself deserves a moment of quiet appreciation here, since so much of what made the International Space Station possible was first learned, often through genuine hardship, aboard this earlier Russian station. Mir's cosmonauts endured genuinely difficult conditions during their long stays in orbit. Equipment failures, a serious onboard fire in 1997, and a collision with an uncrewed cargo vessel that same year, which punctured one of the station's modules and forced the crew to work quickly, calmly, under real pressure to seal off the damaged section and preserve the rest of the station's atmosphere. These difficult experiences, though genuinely dangerous at the time, produced an enormous, invaluable body of practical knowledge about how to actually live, work, and solve emergencies aboard a long-duration space station. Knowledge that Russian engineers would later bring directly into the International Space Station's design and operational procedures, giving the newer, more ambitious station a foundation of hard-won, practical wisdom that no amount of theoretical planning alone could have provided. In the mid-1990s, in a remarkable early preview of the cooperation still to come, American space shuttle missions began docking directly with Mir itself as part of a joint program allowing American astronauts to live aboard the Russian station for extended stay and Russian cosmonauts to fly aboard American shuttle missions. A genuine, practical rehearsal for the far larger, more complex international partnership that would soon follow. The United States, meanwhile, pursued its own station concept, first proposed in 1984 under President Reagan. Originally named Space Station Freedom, an ambitious design that, for years, existed mostly on paper, repeatedly redesigned repeatedly delayed, its budget repeatedly questioned by a Congress unconvinced it could be built as originally envisioned. Then, in 1991, the Soviet Union collapsed. This single historical turning point, more than any single engineering decision, is arguably the true beginning of the station we're building together tonight. With the Cold War rivalry that had driven decades of competing space programs suddenly gone, American and Russian space officials found themselves facing an unusual, almost disorienting new question. What happens now when the two greatest space powers on Earth are no longer trying to defeat each other? The answer, remarkably, was cooperation. In 1993, American and Russian officials began serious negotiations to merge their separate, struggling station programs into a single, shared project. Combining America's space station Freedom design with Russia's decades of practical experience building and operating Mir. This wasn't purely idealistic, it was practical too. Russia's space program, following the Soviet collapse, faced severe funding shortages and needed international partnership to continue its ambitious human spaceflight work. America's Freedom program, meanwhile, needed Russia's proven docking technology, life support systems, and orbital experience to make its own station design realistically achievable within any reasonable budget or timeline. By 1998, this partnership had expanded further, bringing in the European Space Agency, Japan's Space Agency, and Canada, each contributing their own modules, technology, and expertise to what would become, quite literally, the International Space Station. A name chosen deliberately to reflect its unprecedented, genuinely global nature. Rest for a moment in the strangeness of that origin story. A station built not from one nation's singular ambition, the way the pyramid or the Eiffel Tower once were, but from the quiet, practical decision of former rivals to build something together in the empty space above a planet that, from 250 miles up, shows no borders at all. Every structure we've built together in this district so far, the pyramid, the Eiffel Tower, began with a single unified design, refined by one team, constructed at one location, under one clear chain of authority. The International Space Station began nothing like that. Its design instead emerged from 5 separate space agencies: NASA in the United States, Roscosmos in Russia, the European Space Agency representing 11 European nations, JAXA in Japan, and the Canadian Space Agency, each independently designing, building, and testing their own modules in their own countries, according to their own engineering standards, years before any of those pieces would ever physically meet. This created an engineering challenge unlike anything in our previous episodes. Imagine, for a moment, 5 separate teams of builders working in 5 separate countries, each constructing a different section of the very same enormous structure, without ever being able to test fit their pieces together beforehand in real, physical space, because the site where all these pieces would eventually meet wasn't a place any of them could visit during construction. It was orbit, every single connection point, every docking mechanism, every electrical and plumbing interface between one nation's module and another's needed to be specified with a level of precision that made even the Eiffel Tower's 18,000 individually numbered iron pieces look comparatively forgiving. There was no room whatsoever for a piece to arrive and simply be adjusted on site, the way ancient Egyptian masons once fine-tuned casing stones against their neighbors. or the way Eiffel's ironworkers used hydraulic jacks to nudge converging legs into alignment. In space, adjustment happens before launch, or it often doesn't happen at all. To manage this staggering coordination challenge, engineers developed extraordinarily detailed interface control documents. Essentially enormous shared rulebooks specifying the exact dimensions, tolerances, electrical connections, and mechanical requirements for every single point where one agency's hardware would eventually meet another's. These documents needed to be agreed upon years in advance, then followed with religious precision by teams working in different countries, different languages, different engineering cultures, and different measurement systems. American engineers working largely in imperial units, most international partners working in metric, requiring careful, constant translation and cross-checking to avoid the kind of catastrophic mismatch that, in a project like this, couldn't simply be fixed with a wooden wedge and some patient hammering. This is, in its own quiet way, one of the most remarkable feats of the entire project. Not the rockets, not the spacewalks, but the sheer administrative and engineering discipline required to ensure that a module built in a factory outside Moscow would dock perfectly on the first attempt, with the module built in a clean room in Alabama, having never once been tested together until they met in orbit. It's worth slowing down further on just how much quiet, unglamorous coordination this required, since it's easy, when telling a story like this, to focus entirely on rockets and spacewalks and forget the years of careful paperwork and negotiation that made those dramatic moments even possible. Engineers from each partner agency needed to meet regularly, often traveling between Houston, Moscow, Cologne, and Tsukuba, to review interface specifications line by line, resolving disagreements about tolerances, materials, and procedures that might seem, on the surface, almost trivially small, but which carried enormous consequences if left unresolved. A disagreement over something as seemingly minor as the exact torque specification for a particular bolt pattern, or the precise voltage tolerance for a shared electrical connection, needed to be fully resolved years before the actual hardware would ever be built, let alone launched. Because once a module left the ground, there would be no opportunity to renegotiate the physical dimensions of its docking mechanism. Language differences added their own layer of complexity to this already demanding coordination. Russian engineers and American engineers, working from the same interface control documents, needed those documents translated with extraordinary precision, since a subtle mistranslation of a single technical term could introduce exactly the kind of ambiguity this entire painstaking documentation process was designed to eliminate. Many engineers on both sides became genuinely fluent, at least in technical vocabulary, in each other's languages out of sheer practical necessity. A quiet human side of this cooperation story, individual engineers building not just technical understanding, but working relationships and friendships across a linguistic and cultural divide that only a few years earlier their two nations' governments had treated as a genuine geopolitical rivalry. Let's slow down for a while and step inside a different kind of workspace. Not a clean room, not a launch pad, but a mission control center, one of several scattered across the partner nations, each one responsible for monitoring and supporting a specific portion of the station's ongoing assembly and operation. Picture a large, dimly lit room, Rows of computer consoles arranged in careful tiers, each one staffed by a specialist monitoring a specific system. Power, life support, communications, robotics, structural loads, all working together, quietly, continuously, in careful coordination with counterpart teams in other countries, often across significant time zone differences. A flight director. We'll call her Carol, though again, her name is simply a stand-in for the many real people who have held this demanding role over the decades. Sits at the center of this room, wearing a small headset, tracking a live spacewalk currently underway hundreds of miles overhead. Her job today is to maintain a kind of calm, steady oversight across dozens of simultaneous data streams, ready to make quick, careful decisions if anything unexpected arises during the astronaut's work outside the station. Through her headset, she can hear the calm, practiced voice of the spacewalking astronaut, describing their progress as they move, hand over hand, toward the next connection point on a newly arrived truss segment. She can also hear a quieter secondary channel, a counterpart flight director in Moscow, coordinating a separate but related aspect of today's operation. Their conversation passing back and forth through careful, practiced technical shorthand, refined over years of exactly this kind of joint operation. If a problem arises, a slightly elevated reading on a suit's oxygen system, an unexpected resistance encountered while tightening a bolt, Carol's team works quickly and calmly through established procedures, refined across years of previous missions, drawing on the same painstaking documentation and cross-agency coordination we discussed a moment ago. There is no room in a room like this for improvisation born of panic. Every response to every foreseeable problem has already been carefully planned, tested, and rehearsed, long before today's spacewalk ever began, much the way ancient Egyptian surveyors relied on methods tested and refined across generations, rather than inventing their approach fresh with each new pyramid. By the time today's spacewalk concludes, 6 or 7 hours after it began, Carol's shift is far from over. Data must be reviewed, procedures documented, a careful handoff prepared for the next flight director, who will take over monitoring the station through the coming hours. She leaves the control room, eventually, into ordinary daylight or ordinary evening traffic, entirely unremarkable to anyone she passes, having spent her day quietly, carefully helping guide human beings working outside a spacecraft, hundreds of miles above the Earth. Tomorrow, there will be another shift, another spacewalk, another quiet day of careful, practiced vigilance. Rest for a moment in the thought of how many such rooms in how many countries have quietly, continuously supported this station every single day for more than 2 decades now, without a single day of silence. Before any piece of the station could be assembled in orbit, every module first needed to be built, tested, and proven here on Earth. An irony worth sitting with for a moment, since everything about this project's final destination was defined by the complete absence of gravity. And yet every single component still had to survive gravity's full force during construction, testing, and the violent, shaking ascent of launch itself. Zarya, the very first module of the station, was built in Russia at the Khrunichev State Research and Production Space Center in Moscow, a facility with decades of experience building components for Mir and earlier Soviet stations. Unity, the first American-built module, was constructed at a Boeing facility, using components tested extensively at NASA's Marshall Space Flight Center in Huntsville, Alabama. Later modules followed similar patterns. Europe's Columbus Laboratory, built by a consortium of European aerospace companies, coordinated through facilities in Germany and Italy. Japan's Kibo Laboratory, the largest single module on the station, built across multiple Japanese facilities before final assembly and testing near Tokyo. Each of these modules needed to survive an extraordinarily demanding testing regimen before ever being cleared for launch. Vibration testing subjected each module to the violent shaking forces of an actual rocket launch, using massive mechanical shaker tables capable of replicating the specific frequencies and intensities a module would experience riding a space shuttle or Russian Proton rocket into orbit. Thermal vacuum testing placed modules inside enormous chambers capable of replicating the airless void of space. Along with the extreme temperature swings a module would face in orbit, plunging to well below freezing in Earth's shadow, then rapidly heating well above the boiling point of water once exposed directly to unfiltered sunlight. A temperature swing of several hundred degrees repeated over and over every 90 minutes for the module's entire operational life. Every seal, every electrical connection, every mechanical joint needed to survive this brutal thermal cycling without failure, since there would be no atmosphere in orbit to gently moderate temperature swings the way Earth's atmosphere does for us, sitting comfortably right now. Leak testing verified that each module's pressurized hull could reliably hold breathable air against the perfect vacuum of space, with even the smallest undetected leak posing a genuinely serious, potentially fatal risk to future astronauts living inside. Only once a module passed this exhaustive gauntlet of ground testing would it be cleared for the genuinely irreversible next step, being loaded onto a rocket and launched toward a destination where, unlike every structure in our previous episodes, there would be no way to simply climb up and fix a problem by hand, using rope and water and patient human effort, the way builders always had before. Let's slow down for a while and imagine a single ordinary day, not in orbit, not yet, but inside a spotless, brightly lit clean room at a NASA facility. Sometime in the mid-1990s, years before the first module would ever reach space, a young engineer, we'll call her Dana, though we don't know her real name, only that people very much like her formed the quiet backbone of this project, arrives before dawn, changing into a full protective suit before entering the clean room itself, a precaution required to prevent even microscopic dust or skin particles from contaminating sensitive spacecraft components. Inside, the module she's working on today sits partially assembled, its internal wiring harness exposed, waiting for the next stage of careful, methodical installation. Dana's task today involves connecting a specific bundle of electrical wiring to a junction that will, eventually, help regulate temperature control somewhere within the station's life support system. A small, specific piece of an enormously complex whole, much like Etienne's single rivet or the ancient Egyptian quarry workers' single limestone block. Every connection Dana makes today will be checked, then checked again by a separate quality control inspector, then documented in painstaking detail in records that will remain part of the module's permanent technical history, referenced, if necessary, even decades later, should any problem ever arise once the module reaches orbit. There is no room for a close enough here. A single miswired connection, undetected, could mean a life support failure hundreds of miles above Earth with no possibility of the kind of simple, patient, on-site correction that ancient builders once relied upon. Dana works slowly, deliberately, checking her work against detailed schematics at every step, aware in some quiet corner of her mind that this module, this exact piece of hardware she's touching right now, in this ordinary clean room, on this ordinary day, will someday orbit the Earth every 90 minutes, carrying human lives inside it for years, possibly decades, after she completes this single afternoon's careful work. By evening, her task complete and independently verified, she signs the required documentation, changes out of her clean room suit, and drives home through ordinary evening traffic, past ordinary houses, completely unremarkable to anyone who might pass her on the road. A person who spent her day building something that will eventually orbit the entire planet. Tomorrow, there will be another wiring bundle, another junction, another careful, patient step in a testing and assembly process that will span years before this particular module ever sees the inside of a rocket. Rest for a moment in the thought of how many such days, how many Danas in facilities scattered across Russia, America, Europe, and Japan, quietly, patiently, added up to the station, now orbiting above you as you listen to this story tonight. Before we continue following the station's physical assembly, it's worth pausing on one particular engineering challenge that made all of this cooperation actually possible. The docking mechanism itself, the physical hardware allowing two independently built spacecraft to join together, forming an airtight, structurally sound connection without either side ever having tested the fit beforehand on the ground. This might sound, on its surface, like a simple mechanical problem. After all, builders have been fitting pieces together for as long as there has been building. But docking two spacecraft in orbit carries a particular unforgiving set of requirements that ancient stonemasons or even Eiffel's riveters never needed to consider. The connection needed to be airtight, capable of holding pressurized, breathable air securely against the vacuum of space indefinitely, without any possibility of a slow, undetected leak developing over months or years of use. The connection needed to be strong enough to withstand the considerable forces involved in bringing two massive spacecraft together, absorbing the residual momentum of docking without damaging either vehicle. Even though the approaching spacecraft might weigh many tons and be moving, relative to the station, at a speed that needed to be carefully, precisely controlled down to a matter of inches per second. And the connection needed to work correctly on the very first attempt, since there was no opportunity to bring a misaligned or poorly fitted module back down to Earth for adjustment. Russian engineers, drawing on decades of docking experience from the Soyuz and Mir programs, contributed a probe and drog style docking system for many of the station's Russian-built connections, a cone-shaped receptacle on one module, and a matching probe on the approaching spacecraft, designed to guide the two pieces into precise alignment. Even if the initial approach wasn't perfectly centered, the cone's sloped sides gently correcting minor misalignments as the two pieces came together. American and international partners, meanwhile, developed a different standard called the Common Berthing Mechanism, used for many of the station's larger pressurized modules, relying instead on the station's robotic arm to carefully, slowly bring a new module into close alignment before a set of powered bolts drew the two pieces together into a final, secure, airtight seal. Later in the station's history, an even more advanced docking standard was developed specifically to support a new generation of automated and crewed spacecraft, incorporating sensors and guidance systems, allowing for increasingly automated, precise docking, reducing the workload on both the approaching spacecraft's crew and the station's own crew, who in earlier years often needed to carefully monitor and occasionally manually assist an approaching vehicle's final docking sequence. Every one of these docking systems needed to be tested exhaustively on the ground, using specialized facilities capable of simulating the precise mechanical forces involved. Since, just as with every other aspect of this station's construction, there would be no opportunity to simply try again with minor adjustments once the real hardware reached orbit. Once a module passed its exhaustive ground testing, it faced the next enormous challenge: actually reaching orbit. Unlike every structure in our previous episodes, which were built entirely at their final location, the International Space Station's components each needed to survive a genuinely violent journey before construction could even begin. A rocket launch involving forces far more extreme than anything the pyramids, stone haulers, or the Eiffel Tower's riveters ever needed to consider. Two primary launch systems carried station components to orbit during the main assembly period: the American Space Shuttle and Russian Proton and Soyuz rockets. The Space Shuttle, with its large cargo bay, proved particularly valuable for carrying bulky station modules and the enormous truss segments that would eventually form the station's structural backbone. Its distinctive winged orbiter, capable of carrying pressurized modules directly into orbit, then serving as a stable platform from which spacewalking astronauts could carefully maneuver each new piece into position using a robotic arm. Russian Proton rockets, meanwhile, carried several of the station's earliest and most critical modules, including Zarya and later Zvezda, using a launch system with decades of proven reliability, dating back to the Soviet space program's earlier station projects. Each launch represented a genuinely irreversible moment. Once a module left the ground, riding a controlled explosion of enormous force upward through Earth's atmosphere, there was no bringing it back down for adjustment or repair. If something went wrong during ascent, engineers on the ground could only watch, monitor telemetry data streaming back from the ascending rocket, and hope that months, sometimes years, of careful ground testing had genuinely prepared the hardware for this single violent, unrepeatable journey. The timing and sequencing of these launches required its own extraordinary logistical coordination, since modules often needed to arrive in a very specific order, each new piece depending on connections, power, and support systems already established by pieces launched months or even years earlier. A delay in one module's launch schedule could cascade forward, delaying the assembly of pieces that depended on it, creating scheduling ripple effects across a construction timeline that would ultimately span more than a decade, involving dozens of separate launches from facilities on 2 different continents. On November 20th, 1998, a Russian Proton rocket lifted off from the Baikonur Cosmodrome in Kazakhstan, carrying the very first piece of what would become the International Space Station. This first module, named Zarya, a Russian word meaning sunrise or dawn, chosen deliberately to symbolize the beginning of this new era of cooperation, served initially as the station's primary power source and propulsion module, providing the essential electrical and navigational capability needed to keep the earliest pieces of the station stable and functional in orbit. Before additional modules could be added, Zarya's design drew heavily on Russia's decades of experience, building similar functional modules for the earlier Mir space station, giving this crucial first piece a level of proven reliability that would have been far riskier to achieve with an entirely untested new design. For more than 2 weeks, Zarya orbited the Earth alone, an empty, uncrewed module drifting quietly through the darkness and sunlight of each 90-minute orbit, waiting for the next piece of the station to arrive and join it. There is something worth sitting with in that image. A single, solitary module, the very first physical piece of what would eventually become humanity's largest cooperative engineering project, orbiting silently, entirely alone, for those first quiet weeks, much like the very first stone laid at the base of the pyramid or the first iron leg rising alone above the Champ de Mars, before anything else existed alongside it. On December 4th, 1998, just 2 weeks after Zarya's solitary launch, the Space Shuttle Endeavour lifted off from Kennedy Space Center in Florida, carrying the station's second module, Unity, a cylindrical connecting module, sometimes called a node, designed specifically to serve as a docking hub connecting multiple future modules together. This mission, designated STS-88, would accomplish something genuinely unprecedented. The first ever assembly of station components in orbit, requiring astronauts to physically join Zarya and Unity together using the shuttle's robotic arm, then venture outside on spacewalks to complete the electrical and mechanical connections between them. Astronaut Nancy Curry operated the shuttle's robotic arm with extraordinary precision, carefully grappling Unity from the shuttle's cargo bay, then maneuvering it into position to dock with the waiting Zarya module, a delicate, slow-motion ballet of enormous, expensive hardware performed with painstaking care, since any collision between these two pieces could have caused catastrophic damage to a station that, at this point, barely even begun to exist. Once the two modules were successfully mated, astronauts Jerry Ross and James Newman ventured outside on the mission's first spacewalk, floating in the vacuum of space to complete the physical connections between Zarya and Unity, connecting power cables, data lines, and the mechanical latches that would hold the two modules permanently together. This was, in a very real sense, the station's first true construction moment, not unlike the moment the pyramid's 4 surveyed corners were first connected by a taut, measured rope, or the moment the Eiffel Tower's 4 independently built legs first converged successfully at their shared first platform. Except here, the construction site itself was in constant motion, orbiting the Earth at roughly 17,500 miles per hour. The astronauts working in bulky pressurized suits, tethered carefully to prevent themselves from drifting away into the emptiness surrounding them, completing bolt by bolt, connection by connection work using specialized tools designed specifically to function in the airless cold and heat of space, and in the thick, restrictive gloves required to keep a human being alive outside a spacecraft. By the end of this mission, 2 modules, one built in Russia, one built in the United States, designed by teams that had never worked in the same building, coordinated only through those painstakingly detailed interface control documents, we discussed earlier, were successfully joined together, orbiting the Earth as a single connected structure for the very first time. The station, quite literally, had begun. Before we continue following the station's assembly further, it's worth slowing down to properly understand just how fundamentally different this construction process was from anything in our previous episodes. Every technique we've discussed so far in this series, the Egyptian sledges gliding across wetted sand, the Eiffel riveters hammering glowing iron, depended, in one way or another, on gravity, on friction, on the simple, reliable fact that heavy things stay where you put them unless something specifically moves them. None of that applied in orbit. In the near weightlessness of orbital spaceflight, technically called microgravity, objects don't simply rest in place the way they do on Earth's surface. A tool set down on a table doesn't stay there. It drifts slowly in whatever direction it was last moving, potentially floating away entirely if not properly secured. This required an entirely new set of engineering solutions and, just as importantly, an entirely new set of habits and disciplines for the astronauts performing assembly work. Every tool used during station construction needed to be tethered, attached by a small cord or clip to the astronaut's suit or to the structure itself, to prevent it from drifting away during use, since a single dropped tool in orbit doesn't simply fall to the ground where it can be retrieved a moment later. It continues drifting, potentially becoming a genuine hazard, a small but real piece of space debris, moving at orbital velocity, capable of causing serious damage if it later collided with any part of the station. Bolts and fasteners needed specialized designs preventing them from simply floating away once loosened, since a dropped bolt in zero gravity doesn't stay conveniently nearby the way it would on a ground-based construction site. Even body positioning became a genuine engineering challenge. On Earth, a worker naturally braces against gravity, using their own body weight to generate leverage when tightening a bolt or pulling a lever. In microgravity, pushing against something without a secure foothold simply sends the astronaut's own body drifting backward rather than applying useful force to the task at hand. To solve this, station modules were fitted with numerous foot restraints. Simple, sturdy loops and anchoring points, allowing an astronaut to lock their boots securely in place, giving them the stable footing needed to actually apply meaningful force to a task. Much the way a construction worker on Earth relies on simply standing on solid ground. Every single tool, every fastener, every procedure needed to be reconsidered and specifically redesigned for an environment where the most basic assumption of all previous human construction, that things, left alone, stay where gravity puts them, simply didn't apply beyond the tools and fasteners themselves. The single most important piece of equipment in this entire construction process deserves its own quiet, careful attention. The spacesuit itself, without which none of this assembly work outside the station could ever have happened at all. The suits used for station spacewalks, formerly called extravehicular mobility units, represent an extraordinary feat of engineering in their own right, functioning essentially as a small, self-contained spacecraft built to fit around a single human body. Each suit consists of multiple layers, beginning with an inner garment that circulates cool water through a network of thin tubing directly against the astronaut's skin, carrying away the substantial body heat generated by hours of physical exertion. Since the vacuum of space despite popular imagination, doesn't actually cool a working human body efficiently on its own. There's no air present to carry a heat away through ordinary convection, the way a cool breeze might on Earth. Surrounding this cooling garment, a pressurized inner layer maintains a stable internal air pressure around the astronaut's body, since the true vacuum of space would otherwise cause the fluids in an unprotected human body to boil at normal body temperature, a genuinely fatal consequence within seconds of exposure. An outer layer of the suit provides protection from the extreme temperature swings between direct sunlight and orbital shadow, from micrometeorite impacts, and from the sheer physical wear of the suit brushing repeatedly against the station's metal handrails and structure during hours of careful, deliberate movement. The suit's helmet includes a sun visor that can be lowered to protect the astronaut's eyes from direct, unfiltered sunlight, far more intense in orbit than anything experienced on Earth's surface, where our atmosphere filters and diffuses sunlight before it ever reaches our eyes. Perhaps most remarkably, each suit contains its own miniature life support backpack, providing oxygen, removing exhaled carbon dioxide, monitoring the astronaut's vital signs, and maintaining communication with both their spacewalking partner and mission control on the ground. An entire self-sufficient survival system, compact enough to be worn on a single person's back, yet reliable enough to be trusted with a human life for 6, 7, sometimes 8 hours at a stretch, floating entirely alone in the vacuum of space. The suit's gloves deserve particular mention, since they represent one of the most persistent, genuinely difficult engineering challenges in the entire design. Pressurized gloves naturally want to remain puffed outward, resisting an astronaut's attempt to close their fingers, much the way an inflated balloon resists being squeezed into a fist. Every finger movement, every attempt to grip a tool or turn a bolt requires the astronaut to work against this constant resistance, hour after hour, a genuinely exhausting physical demand that often leaves astronauts with sore hands and fingertips even after a successful, otherwise uneventful spacewalk. Engineers have spent decades refining glove designs specifically to reduce this fatigue, incorporating careful joint designs at each knuckle, allowing slightly easier movement. Though the fundamental physics of working inside a pressurized glove in the vacuum of space remains one of the quieter. Every single spacewalking astronaut has needed to physically endure spacewalk after spacewalk throughout the station's entire assembly history, before any astronaut ever floated outside the station on a real spacewalk or operated Canadarm2 to maneuver a genuine multi-ton module into position. They spent years, quite literally years, training for tasks that, at the time of their training, existed only as blueprints, models, and careful simulations, since, for much of the assembly period, the specific module or truss segment they were training to install hadn't yet been built, let alone launched. This training took place across several remarkable facilities, each addressing a different piece of the puzzle. At NASA's Neutral Buoyancy Laboratory near Houston, astronauts trained inside an enormous indoor pool containing a full-scale mock-up of the station's modules, submerged underwater to approximate, though never perfectly replicate, the sensation of weightlessness. Wearing full spacesuits underwater, astronauts practiced the exact sequence of movements they would eventually perform in orbit, carefully choreographed and repeated dozens of times until each motion became second nature, since there would be no opportunity during the real spacewalk itself to pause and reconsider an unfamiliar task. This underwater training, while remarkably useful, never perfectly replicated true microgravity. Water resistance still slows movement in ways the true vacuum of space does not, and buoyancy can be carefully adjusted but never precisely matches the sensation of genuinely floating, completely unconstrained in 3 dimensions. To supplement this underwater training, astronauts also spent time aboard specially modified aircraft, flying steep parabolic arcs, creating brief periods, typically less than a minute at a time, of genuine weightlessness, allowing astronauts a small, precious glimpse of true microgravity before their actual mission. A training aircraft nicknamed with a certain dark humor common among test pilots and astronauts alike, the Vomit Comet. Acknowledging the genuine physical discomfort many trainees experienced during these repeated, brief plunges into weightlessness. Russian cosmonauts underwent similarly rigorous training at Star City, outside Moscow, a dedicated training facility with its own long history dating back to the earliest days of the Soviet space program, including specialized simulators for the Soyuz spacecraft's docking procedures and extensive classroom study of the station's Russian-built systems. International partner astronauts representing Europe, Japan, and Canada typically trained across multiple facilities in multiple countries, learning not just the technical procedures for their own contributed hardware, but also the American and Russian systems they would need to operate and understand as full working members of an international crew. This meant that by the time any individual astronaut finally launched toward the real station, they had typically spent years training across facilities in Houston, Star City, Cologne, and Tsukuba, learning to speak enough Russian or English, depending on their native language, to communicate clearly and precisely with crewmates and ground teams from entirely different countries and cultures, in situations where a simple miscommunication could carry genuinely serious consequences. There is something worth appreciating quietly in just how much invisible preparation stands behind every single spacewalk, every single robotic arm operation, every single module installation we've discussed throughout tonight's story. Years of underwater practice, brief, precious minutes of true weightlessness aboard a lurching training aircraft, careful cross-cultural and cross-linguistic preparation, all invested long before a single bolt was ever actually tightened in the true vacuum of space. Beyond the technical training and careful engineering coordination, there is a quieter, more human dimensions to this international cooperation worth sitting with tonight, one that reveals itself most clearly, not during a dramatic spacewalk, but during something as ordinary as a shared meal. Astronauts and cosmonauts living together aboard the station for months at a time inevitably develop close, genuine working relationships. Despite coming from entirely different countries, cultures, and, in many cases, entirely different first languages, meals aboard the station often become a small, informal celebration of this diversity. Crew members sharing food brought from their home countries alongside the station's standard supply of rehydratable meals. A Russian cosmonaut offering canned fish and rye bread, carried up on a recent Progress resupply vehicle, an American astronaut sharing care packages of freeze-dried fruit or chocolate sent up by family, a Japanese astronaut occasionally treating crewmates to specially packaged versions of familiar dishes from home, adapted carefully to survive the demands of space food packaging and preparation. These shared meals, floating gently around the station's small dining table, secured by the same Velcro and restraint systems, keeping everything else from drifting away, often become genuine highlights of the crew's day, a small, deliberate ritual of togetherness in an environment that could otherwise feel isolating, hundreds of miles removed from family, friends, and the familiar comforts of life on Earth. Birthdays and holidays are celebrated aboard the station too. Crews marking occasions like Christmas, Thanksgiving, or Russian Orthodox holidays together, regardless of which crew member's home culture the particular holiday originates from. A small, genuine gesture of inclusion that mirrors, in its own modest way, the larger spirit of cooperation that brought this station into existence in the first place. Language barriers, while genuinely present, particularly during the station's earlier years, before extensive cross-training became standard practice, are typically bridged through a combination of practiced technical vocabulary, patient repetition, and simple goodwill. Astronauts and cosmonauts alike describing a kind of hard-won fluency in communicating clearly and warmly with crewmates, even when neither party is speaking their true native language. There's a quiet, meaningful detail worth remembering here. The very cultures whose governments, only a few decades ago, viewed each other as Cold War adversaries, now share simple, ordinary meals together, floating gently around a small table, hundreds of miles above a planet that, from their shared vantage point, shows no evidence at all the borders and rivalries that once divided their nations so sharply. Let's slow down further and follow a single spacewalk from beginning to end, much the way we followed Etienne's day at the Eiffel Tower, or the granite block's long journey down the Nile, hours before the spacewalk itself begins. Two astronauts start a careful, lengthy preparation process called pre-breathing, spending time breathing pure oxygen at reduced pressure, gradually adjusting their bodies to avoid decompression sickness. Once they transition from the station's normal internal atmosphere to the low-pressure environment inside their spacesuits. This process alone can take several hours, requiring patience and careful monitoring, not unlike the caisson workers who once needed careful decompression procedures beneath the Eiffel Tower's riverside foundation a full century earlier. Once properly prepared, each astronaut is helped into their spacesuit, technically called an extravehicular mobility unit, an extraordinarily complex, multi-layered garment functioning essentially as a small personal spacecraft, providing oxygen, temperature regulation, communication, and protection from both the vacuum of space and the extreme temperature swings of direct sunlight versus orbital shadow. Suiting up alone can take the better part of an hour, with a fellow crew member carefully checking every seal, every connection, every system readout, since even a small, undetected fault in this suit represents a genuinely life-threatening risk once the astronaut floats outside the station's protective hull. Once suited and pressure-checked, the astronauts enter the station's airlock, a small chamber that can be sealed off from the rest of the station's internal atmosphere, then slowly depressurized until it matches the vacuum of space outside, at which point the outer hatch can finally, safely, be opened. And then the astronaut floats outside. Imagine it slowly for a moment. Earth spread out below, a vast, curved, brilliant blue horizon, clouds drifting silently across oceans and continents, the entire planet visible at once in a way no previous builder in human history, not the pyramids' careful surveyors, not Eiffel's riveters balanced hundreds of feet above Paris, could have ever imagined witnessing with their own eyes. Above, below, and all around only the deep black stillness of space, utterly silent except for the astronauts' own breathing and the quiet hum of their suits' life support systems. The astronaut, carefully tethered, begins making their way, hand over hand, along the station's exterior handrails toward their assigned work site for today's spacewalk. Perhaps installing a new truss segment, perhaps connecting cabling for a newly arrived module, perhaps performing routine maintenance on the station's solar arrays. Every movement must be slow, deliberate, and carefully considered, since such forceful movements in a pressurized suit in microgravity can easily send an astronaut tumbling or drifting in unintended directions, wasting valuable time and oxygen correcting course. Communication with mission control on the ground continues throughout, astronauts describing their progress, ground teams monitoring suit systems, offering guidance, occasionally troubleshooting an unexpected problem in real time, hundreds of miles below. A single spacewalk can last anywhere from 5 to 8 hours. Astronauts working steadily, carefully, through a meticulously planned sequence of tasks, each one rehearsed extensively beforehand in massive underwater training pools back on Earth, where the buoyancy of water can approximately simulate, though never perfectly replicate, the sensation of working in true microgravity. By the time the spacewalk concludes and the astronauts return to the airlock, they are often physically and mentally exhausted. Hours of careful, deliberate physical effort performed inside a stiff, pressurized suit, demanding constant concentration and precision, with absolutely no room for the kind of careless mistake that, in this environment, could prove fatal. And yet, spacewalk by spacewalk, year after year, this is precisely how the station's most complex structural elements, its trusses, its solar arrays, its external equipment, were actually assembled hundreds of miles above the Earth entirely by hand, much like Etienne's rivets or the pyramid workers' careful, patient stonework, simply relocated to an environment no previous builder in human history had ever needed to consider. Following the successful docking of Zarya and Unity, the station's assembly continued steadily, though not without genuine delay and difficulty. The next critical module, Russia's Zvezda service module, faced significant delays due to funding difficulties within Russia's space program during this turbulent post-Soviet period. A reminder that even the most carefully engineered project remains vulnerable to the very ordinary, very human problem of simply running short on money at a critical moment. Zvezda finally launched in July of 2000, nearly 2 years after Zarya's initial launch, providing crucial living quarters, life support systems, and propulsion capability that would allow the station to finally support long-term human habitation, rather than existing merely as an uncrewed, if steadily growing, orbital structure. With Zvezda successfully docked, the station was finally ready to welcome its first long-term resident crew. On November 2nd, 2000, astronaut William Shepard and cosmonauts Yuri Gidzenko and Sergei Krikalev arrived aboard the station, beginning what would become an unbroken, continuous human presence in orbit that continues, remarkably, to this very day, meaning that for more than 2 decades now, without a single gap, human beings have been living and working aboard this station, circling the Earth every 90 minutes, day and night, without pause. This first crew, designated Expedition 1, faced genuinely demanding conditions. The station, at this early stage, remained far from complete, a partial structure, still steadily growing, module by module, launch by launch, with the crew themselves often assisting directly in the ongoing assembly and activation of new sections as they arrived. There is something worth appreciating, quietly, in the fact that this station has never once, in over 2 decades, been left completely empty, unlike the pyramid, sealed and left for millennia, or the Eiffel Tower, standing empty through countless quiet nights. The International Space Station has maintained a continuous, unbroken human heartbeat since that very first crew arrived in November of 2000. Someone, somewhere aboard that structure, is awake or asleep, working or resting, at this exact moment as you listen to this story. Through the early 2000s, the station's assembly continued at a steady, carefully planned pace, with space shuttle missions delivering an increasing number of components, particularly the enormous truss segments that would eventually form the station's structural backbone, a long, girder-like framework stretching more than the length of an American football field, once fully complete. These truss segments served a purpose somewhat similar to the Eiffel Tower's carefully calculated iron lattice, providing structural rigidity and support, while also serving as the mounting framework for the station's enormous Sotera allays, the wing-like panels responsible for generating all of the station's electrical power directly from sunlight. Assembling this truss structure required some of the most physically demanding and logistically complex spacewalks of the entire program. Astronauts working methodically to bolt together massive segments, each one requiring the Space Shuttle's robotic arm, and later the station's own robotic arm, Canadarm2, to carefully maneuver into position before spacewalking astronauts could complete the final connections. Canadarm2, contributed by the Canadian Space Agency, deserves particular attention here, since it represents one of the station's most quietly essential pieces of construction equipment, a sophisticated robotic arm, capable of walking hand over hand along specialized grapple fixtures positioned across the station's exterior, allowing it to reposition itself anywhere along the growing structure rather than remaining fixed in a single location the way Earth-based construction cranes typically do. It's worth slowing down further to appreciate just how remarkable this walking capability truly is, since it solved a problem that, in many ways, echoes the self-climbing crane system Eiffel's engineers once devised for their own tower more than a century earlier. A conventional crane, fixed to a single base, can only reach as far as its own arm allows. Canadarm2, instead, has an identical, symmetrical grapple fixture at each end of its arm, allowing it to essentially release its backhand, swing its entire body around its front hand, then grip a new fixture a point further along the station structure, repeating this deliberate, careful, inchworm-like movement to relocate itself gradually across the station's entire exterior, without ever needing to be physically uninstalled and reinstalled at a new location. This arm measures over 50 feet in length, with 7 motorized joints providing it flexibility roughly comparable to a human arm and shoulder combined, allowing it to grip, rotate, and precisely position multi-ton objects with a level of control that would be genuinely difficult for human hands alone, even with the benefit of careful tethering and foot restraints. Astronauts operating Canadarm2 from inside the station work at a specialized robotics workstation, using video feeds from cameras mounted along the arm itself, along with cameras positioned around the station's exterior to carefully judge distances and alignment, a task requiring genuine skill and extensive training, since misjudging the arm's position, even slightly, when maneuvering a massive, expensive module close to the station's existing structure could result in a genuinely serious collision. This robotic arm performed much of the heavy lifting, quite literally, throughout the station's assembly, grappling newly arrived modules and truss segments from visiting spacecraft, then carefully, slowly, maneuvering them into position for astronauts to complete final bolting and connection work, functioning as an indispensable partner to the humans' spacewalkers, extending their reach and lifting capability far beyond what human hands and tethers alone could safely manage. Later in the station's operational life, a smaller, more dexterous robotic device, nicknamed Dextra, was added specifically to handle finer, more delicate tasks, swapping out smaller equipment packages, performing routine maintenance tasks that once would have required a full human spacewalk, reducing the physical risk and time burden on the station's human crew for certain categories of external work. Together, these robotic systems represent a genuinely new category of construction tool, one entirely absent from our previous 2 episodes, not a replacement for human hands, but a careful, precise extension of them, allowing astronauts to accomplish tasks that would otherwise have demanded even more spacewalks, more time in that stiff, demanding pressurized suit, more exposure to the genuine risks inherent in working unprotected in the vacuum of space. The solar arrays themselves, once fully unfurled, form some of the largest man-made structures ever operated in space, together capable of generating well over 100 kilowatts of electrical power, enough to comfortably power dozens of typical homes, collected directly from sunlight and distributed throughout the station's various modules and systems. Each new truss segment and solar array addition brought the station closer to its final, planned configuration, though the overall assembly timeline remained subject to the same kind of scheduling pressures and occasional setbacks, familiar from our previous episodes, funding questions, technical delays, and, as we'll discuss next, a genuinely serious tragedy that would, for a time, halt the entire program. Let's slow down for a while and shift our attention away from orbit entirely, down to the ground, to a quiet launch viewing area at Kennedy Space Center on the morning of one of these many truss segment delivery missions. A woman stands among a small crowd of family members, gathered at a respectful distance from the launch pad, watching the space shuttle standing upright against the early morning sky, steam gently venting from its fuel tanks as the final countdown approaches. Her husband is aboard, seated inside the shuttle's cabin, strapped securely into his seat, waiting through these final tense minutes before liftoff, minutes he has trained for across years of preparation in Houston's underwater training pool. In the lurching cabin of the parabolic training aircraft, in countless hours of simulator practice, rehearsing every conceivable problem that might arise during today's mission. She has been through this before, this particular kind of waiting, though it never quite becomes fully comfortable, no matter how many times she experiences it. A mixture of genuine pride and quiet, private worry, held carefully in check as the countdown clock ticks down towards zero. When the engines finally ignite, the sound arrives a moment after the light. A bright, sudden flare beneath the shuttle, followed by a physical wave of sound and vibration that she feels in her chest before she consciously registers it in her ears. The enormous vehicle lifting slowly, then with startling speed, arcing up and away over the Atlantic coastline, a bright trail of exhaust marking its path long after the vehicle itself has become too small to clearly see. Within minutes, her husband will be in orbit. Within a few days, he'll be helping to install another piece of the growing station's truss structure. Floating outside in his pressurized suit, hundreds of miles above the very launch pad she's standing at right now. She'll speak with him briefly later in the mission through a scheduled video call, hearing about the spacewalk in his own calm, practiced, understated way, the enormous danger and difficulty of the work carefully softened in the retelling. The way it so often is between people who love each other and don't wish to worry one another more than necessary. This quiet, human dimension of the story, the families watching from the ground, carrying their own private version of the risk and pride wrapped up in this entire project, rarely makes it into the technical histories of truss segments and solar array specifications. But it's worth remembering tonight that behind every single spacewalk, every single successful docking, every single piece of this enormous cooperative station, there was also someone standing on the ground, somewhere, watching, waiting, hoping for a safe return. On February 1st, 2003, the Space Shuttle Columbia broke apart during re-entry into Earth's atmosphere, killing all 7 astronauts aboard. A devastating tragedy that, beyond its immediate human loss, profoundly affected the station's ongoing construction timeline. Following this accident, NASA grounded the entire Space Shuttle fleet for more than 2 years. While investigators worked to understand exactly what had gone wrong, and engineers worked to implement the safety improvements needed before shuttle flights could safely resume. This grounding created a genuinely serious challenge for the station's assembly. The Space Shuttle had been the primary vehicle for delivering the station's largest components, pressurized modules and enormous truss segments, and without it, station assembly slowed dramatically, relying instead on smaller Russian Soyuz and Progress spacecraft, capable of ferrying crew and essential supplies, but far too small to carry the large modules still awaiting launch. During this extended pause, the station's crew size was temporarily reduced, and its continued operation depended almost entirely on Russia's proven, reliable Soyuz and Progress spacecraft, a genuine testament to the value of the station's fundamentally international, multi-vehicle design. Since a station dependent on only a single nation's launch capability might have faced a far more serious crisis during this difficult period. When shuttle flights finally resumed in 2005, and particularly once full assembly missions resumed in earnest by 2006, the station's construction accelerated significantly. Engineers and astronauts working to make up for lost time, while incorporating important new safety procedures developed in response to the Columbia tragedy, including detailed on-orbit inspection techniques allowing crews to carefully examine their shuttle's heat shield for damage before committing to the return journey home. There's something worth sitting with quietly in this chapter of the station's story. Unlike the pyramid or the Eiffel Tower, whose construction, however difficult, never faced the loss of human life during the building process itself, the station's assembly exists within the shadow of genuine, serious risk. A reminder that this particular construction project, more than any other in our series so far, asked its builders to accept a level of personal danger unmatched by ancient quarry work or even the riveters balanced high above Paris. The station that continues orbiting peacefully above us tonight carries, within its history, both remarkable international cooperation and the memory of genuine sacrifice. Following the resumption of full assembly missions, the station's construction proceeded through its final major phase, incorporating some of its most scientifically significant components. Europe's Columbus laboratory module launched in February of 2008, providing European researchers with a dedicated space for conducting scientific experiments across biology, physics, and materials science in the unique environment of sustained microgravity. This module, built through a consortium involving companies and research institutions across 11 European nations, represented years of careful, coordinated design work, its final assembly and testing completed in Bremen, Germany, before being shipped to Kennedy Space Center for launch. Itself a smaller echo of the same kind of cross-border coordination that defined the entire station's construction. Once installed, Columbus quickly became a hub for a remarkable range of European-led scientific investigations, from studies of how flames behave differently in microgravity to experiments examining bone density loss in greater detail, to as experiment platforms mounted on the module's exterior, exposing samples directly to the radiation and vacuum of space to study their long-term effects. Japan's Kibo Laboratory, the largest single module aboard the station, arrived across 3 separate launches between 2008 and 2009, given its considerable size, a testament to just how enormous and complex some of the station's individual components had become by this later stage of assembly, requiring multiple missions simply to deliver and assemble one nation's contribution. Kibo's name, fittingly, means hope in Japanese, chosen to reflect the same spirit of optimistic international cooperation that had, by this point in the station's history, carried the project successfully through the Columbia tragedy and years of careful, patient assembly work. Kibo's design even included an external porch, officially called the exposed facility, allowing experiments and equipment to be positioned directly outside the station's pressurized hull, exposed to the true vacuum and radiation of space, robotically maneuvered into place, using specialized equipment developed specifically for this purpose, since even the trained spacewalking astronauts couldn't reasonably spend extended time manually installing every single external experiment package. This module also included its own small robotic arm, developed by Japanese engineers specifically to handle the delicate task of moving experiments between Kibo's internal pressurized laboratory and its external, exposed platform. Yet another example of the quiet, specialized robotics that, throughout this entire project, extended and supported the careful, limited hours available for direct human spacewalking labor. By 2011, following the successful delivery and assembly of these major laboratory modules and the completion of the station's full truss and solar array structure, the station had essentially reached its planned full configuration. A sprawling, complex structure roughly the size of an American football field, including its solar arrays, orbiting the Earth continuously, hosting a permanent international crew representing the combined engineering effort of more than a dozen countries across more than a decade of continuous construction. The Space Shuttle program itself concluded in 2011, its final flights largely dedicated to delivering the station's last major components and supplies before the entire shuttle fleet was permanently retired, its essential role in the station's construction complete. Before we settle into the station's finished, everyday rhythms, it's worth slowing down to appreciate the quiet, constant machinery working day and night, simply to keep human beings alive in an environment that offers absolutely nothing a human body needs to survive. Unlike every previous structure in our series, built in places where air, water, and reasonably tolerable temperatures were simply freely available, the International Space Station exists inside the vacuum of space, where there is no air to breathe, no liquid water, and temperatures swinging between extremes, far beyond anything the human body could survive unprotected even for a few seconds. Every single one of these basic survival needs required careful, dedicated engineering, refined across the entire assembly period, and continuously improved throughout the station's operational decades since. The station's atmosphere is carefully maintained at a pressure and an oxygen composition closely matching what we breathe comfortably here on Earth's surface, generated partly through onboard oxygen generation systems that split water into oxygen and hydrogen through electrolysis, and partly through carefully scheduled resupply missions carrying additional oxygen and nitrogen from Earth. Carbon dioxide, produced constantly by the crew's own breathing, must be continuously scrubbed from the station's air using dedicated filtration systems. Since even a modest buildup of carbon dioxide in a sealed environment can quickly become dangerous, causing headaches, impaired thinking, and worse, if allowed to accumulate unchecked. Water management aboard the station represents one of its most genuinely remarkable engineering achievements. A closed-loop recycling system that reclaims and purifies water from multiple sources, including the crew's own urine, sweat, and even moisture that condenses from their simple breathing, processed through multiple stages of filtration and purification until it emerges cleaner in many respects than much of the tap water available in ordinary homes here on Earth. This closed-loop water system typically recovers well over 90% of the water aboard the station, dramatically reducing the enormous cost and difficulty of launching fresh water supplies from Earth. Every kilogram of cargo launched to orbit carries a considerable expense, making genuine, careful recycling not simply an environmental preference, but an absolute practical necessity for any long-term human presence in space. Temperature control requires its own continuous, careful management, since one side of the station, facing direct sunlight, can heat dramatically, while the shadowed side simultaneously plunges toward the deep cold of space. all while the station itself completes a full orbit, and therefore a full transition between sunlight and shadow every 90 minutes. Dedicated radiator panels extending outward from the station's truss structure continuously release excess heat generated by the station's electrical systems and its human occupants, while internal cooling loops carefully circulate fluid throughout the station's various modules, keeping temperatures within the narrow, comfortable range human bodies and sensitive electronic equipment both require. Food aboard the station arrives primarily through regular resupply missions, carefully packaged to survive the vibration and pressure changes of launch, along with the station's own limited but genuinely meaningful experiments in growing fresh vegetables directly aboard, using specialized growth chambers with carefully controlled lighting, water delivery, and nutrient supply. A small hopeful step toward the kind of self-sufficiency future longer duration missions to Mars or beyond will eventually require. There is something worth appreciating quietly in just how much careful, continuous engineering effort goes into simply maintaining the basic conditions for human life aboard this station. Conditions that, here on Earth, we rarely think about at all, since our planet provides them freely, continuously, without any need for filtration systems, electrolysis units, or carefully scheduled resupply missions. The pyramids builders never needed to manufacture their own air. The Eiffel Tower's riveters never needed to recycle their own drinking water. The station's crew, quietly, continuously, depends on exactly this kind of careful, redundant, constantly monitored machinery, simply to remain alive long enough to continue the scientific work that justifies the station's existence in the first place. With major assembly complete, the station transitioned into its ongoing operational phase, hosting continuous rotating crews conducting scientific research across an enormous range of disciplines: biology, physics, medicine, material science, and Earth observation, taking full advantage of the unique, sustained microgravity environment that no ground-based laboratory could ever replicate. Life aboard the station settled into its own particular rhythms, astronauts typically spending 6 months at a time in orbit, following carefully structured daily schedules, balancing scientific work, station maintenance, mandatory exercise to counteract the muscle and bone loss that comes from extended time in microgravity, and, importantly, personal rest. The station orbits the Earth roughly every 90 minutes, meaning its crew experiences 16 sunrises and 16 sunsets every single day. An extraordinary, almost dreamlike rhythm entirely unlike anything experienced by any previous builder in our series, whose work, however demanding, was always still governed by Earth's familiar, single daily cycle of sunrise and sunset. It's worth pausing here, quietly, to ask a question we haven't yet fully addressed tonight. Why build any of this at all? Why assemble thousands of engineers, 5 separate national space agencies, and hundreds of billions of dollars in combined investment, simply to construct a laboratory floating 250 miles above the Earth? The answer, in part, lies in the genuinely unique nature of the environment itself. Sustained microgravity allows scientists to study physical, chemical, and biological processes in ways simply impossible anywhere on Earth's surface, where gravity constantly influences how fluids mix, how flames burn, how crystals form, and how living cells grow and organize themselves. Materials science experiments aboard the station have produced crystals of remarkable purity, useful for understanding protein structures relevant to developing new medications, grown in an environment where gravity-driven convection and sedimentation, which normally introduce subtle imperfections during crystal growth on Earth, simply don't interfere in the same way. Medical research aboard the station has provided crucial insight into bone density loss, muscle atrophy, and cardiovascular changes that occur during extended spaceflight. Research considered absolutely essential for planning any future, longer-duration human missions to Mars or beyond, since a journey to Mars would expose astronauts to months of continuous microgravity, far exceeding even the station's own typical 6-month rotations. Combustion studies aboard the station have revealed that flames burned differently in microgravity, forming small spherical shapes rather than the familiar teardrop shape flames take on Earth. Insights with genuine practical relevance for improving fire safety and combustion efficiency in engines and industrial processes back on the ground. Earth observation, too, represents a significant part of the station's ongoing scientific mission, with specialized cameras and sensors mounted on the station's exterior, continuously monitoring weather patterns, natural disasters, and long-term environmental changes across the entire planet, providing researchers with a uniquely comprehensive, continuously updated vantage point unavailable from any single ground-based location. Beyond the purely scientific value, though, there is something else worth considering tonight. Something less easily measured in published research papers or patent filings. The International Space Station stands as a genuine, sustained proof that nations once locked in open rivalry can choose, instead, patient, careful cooperation. Not merely as a one-time diplomatic gesture, but as a continuous functioning daily reality, maintained successfully across more than 2 decades through economic hardships, political tensions, and even, at times, open conflict between certain partner nations here on Earth below. Whatever disagreements arise between the station's partner governments on the ground, the station itself has continued operating, continuously crewed, continuously cooperative, a quiet, orbiting demonstration that shared purpose, however imperfectly, can outlast even genuine political friction. Astronauts often describe looking out the station's windows during quiet moments as one of the most profound, meditative experiences of their entire time in space. Watching entire continents drift silently past below, city lights glittering across the night side of the planet, auroras shimmering green and violet near the poles, all in complete peaceful silence, broken only by the quiet hum of the station's own life support systems. There is a particular module called the cupola, contributed by the European Space Agency, specifically designed as an observation deck. A cluster of windows offering a genuinely panoramic view of Earth below, installed 2010, giving astronauts, for the first time in the station's history, a dedicated, comfortable space simply to sit quietly and watch the planet turn beneath them. Much like Gustav Eiffel's own private apartment near the Eiffel Tower's summit, offering him a similarly unique vantage point over Paris. The cupola offers the station's crew their own quiet space for reflection, high above everything and everyone they know. orbiting a planet that, from this vantage point, shows no visible borders, no visible conflicts, no visible evidence at all of the very rivalry that once inspired this station's earliest competing origins. Let's slow down once more and follow a single ordinary day aboard the finished station. Not a dramatic spacewalk, not a tense docking, just an average Tuesday, somewhere in the station's second decade of continuous operation. An astronaut wakes gently inside their small, personal sleeping compartment, roughly the size of a phone booth, secured to one wall of a module, their sleeping bag tethered loosely to prevent them from drifting during the night. There is no true down in this compartment, no particular orientation required, though most astronauts find it comforting to sleep with some sense of up and down established by the module's visual layout, even if their body technically floats freely inside their tethered bag. A gentle alarm, set according to Greenwich Mean Time, the shared reference time used aboard the station regardless of which country's module a crew member happens to be sleeping in, signals the start of the day. Breakfast is eaten from a carefully packaged tray, food secured with Velcro and magnets to prevent it from drifting away mid-meal, the astronaut perhaps enjoying a rehydrated meal alongside a pouch of coffee, sipped carefully through a specially designed straw and valve system, since a floating, escaped droplet of hot coffee is a genuine minor hazard around sensitive electronic equipment. The morning begins with a mandatory exercise session, roughly 2 hours in total spread across the day, using specialized equipment, including a treadmill fitted with a harness system holding the astronaut down against the running surface, and a resistance exercise device using vacuum cylinders rather than free weights, since weights in microgravity offer no resistance at all on their own. This daily exercise isn't optional or merely recreational. It's a genuine medical necessity, carefully monitored by flight surgeons on the ground, essential for maintaining bone density and muscle mass that would otherwise deteriorate significantly during extended time in microgravity. Following exercise, the astronaut typically spends several hours conducting whatever scientific experiments are scheduled for that particular day. Perhaps monitoring a materials science experiment in the Destiny laboratory module, perhaps tending to plant growth chambers, perhaps assisting a ground-based research team monitoring a medical study on the effects of long-duration spaceflight on the human body, using their own body, in many cases, as part of the very data being collected. A midday meal follows similar careful preparation to breakfast, astronauts often gathering together around the station's small dining area, sharing a meal much the way any workplace colleagues might, floating gently around a shared table secured with the same Velcro and magnetic fasteners, keeping their food from drifting away. Afternoons often bring more scientific work, station maintenance tasks, or preparation for upcoming spacewalks, or the arrival of a resupply vehicle, astronauts working through carefully scheduled task lists coordinated with mission control teams on the ground. Much like Carol's team we visited a little earlier tonight, evenings offer a small amount of personal time. Astronauts often describe this quiet period as their favorite part of the day, using it to write personal journals, speak with family back on Earth through scheduled video calls, or simply float quietly in the cupola module, watching the planet turn slowly beneath them. City lights and lightning storms and the shifting colors of dawn and dusk repeating themselves 16 times over in the span of a single ordinary day. By the time the astronaut returns to their small sleeping compartment for the night, they will have experienced 16 sunrises and 16 sunsets, a rhythm entirely unlike anything a human body evolved to expect, and yet one that astronauts consistently describe adapting to with surprising ease. The station's steady, structured daily schedule providing enough familiar routine to anchor them, even as the actual light outside their window cycles far more rapidly than anything in ordinary human experience. Tomorrow, there will be another set of experiments, another exercise session, another shared meal, another quiet evening in the cupola. Rest for a moment in the thought of just how ordinary, in its own particular way, life aboard this extraordinary structure has become. A testament, perhaps, to how readily human beings can adapt to even the strangest, most demanding environments, given enough careful engineering and enough patient, steady routine. The International Space Station has now orbited the Earth for well over 2 decades, completing more than 100,000 individual orbits since Zarya's solitary launch in November of 1998. In that time, it has hosted astronauts and cosmonauts from nearly 20 different countries, representing one of the most sustained successful examples of international cooperation in human history, continuing steadily even through periods of considerable political tension between its partner nations here on Earth below. It witnessed the transition from space shuttle to a new generation of American commercial crew vehicles, developed specifically to continue supporting the station once the shuttle program concluded in 2011. It witnessed the aging and eventual carefully controlled deorbiting of its old companion, the Russian Mir station, guided safely into the Pacific Ocean in 2001. Its decades of pioneering long-duration spaceflight experience having directly informed much of the International Space Station's own design and operational procedures. It witnessed record-breaking stays by individual astronauts, including missions lasting nearly a full year, providing crucial medical data on the long-term effects of space travel on the human body, data considered essential for humanity's eventual, more ambitious future journeys toward Mars and beyond. It witnessed the arrival of new commercial cargo and crew vehicles throughout the 2010s and 2020s, as private companies began taking on a growing share of the station's supply and crew rotation responsibilities, a new chapter in orbital construction and logistics that Zarya's original Russian and American builders back in 1998 could scarcely have fully anticipated. Much like the pyramid quietly witnessed the rise and fall of empires from its fixed position in the desert, and the Eiffel Tower quietly witnessed the rise and fall of world wars from its fixed position above Paris. The International Space Station witnesses history from a vantage point genuinely unlike anything in our previous episodes. Not fixed in place at all, but constantly moving, circling the entire planet every 90 minutes. Watching continents and oceans and cities drift silently beneath it, indifferent in its steady orbit to the borders and conflicts of the world below. Let's pause for a moment and walk back through the full sweep of the station's assembly timeline, slowly, quietly, the way you might look back over the years of your own life before finally settling into sleep. November 1998. Zarya launches alone drifting quietly through empty orbit for 2 solitary weeks. December 1998. Unity arrives, and the very first connection is made, hand over hand in the vacuum of space. July 2000. Zvezda finally arrives, following lengthy funding delays, providing the crucial life support systems needed for permanent habitation. November 2000. The first long-term crew arrives, beginning an unbroken human presence that continues to this day. Through 2001, the station's first major truss segment and solar array arrive, along with Destiny, the American laboratory module, giving the station its first dedicated space for serious scientific research. Through 2002, assembly continues steadily. Additional truss segments extending the station's growing structural backbone, section by section, much like the Eiffel Tower's iron legs once rose section by section above the Champ de Mars. February 2003. The Columbia tragedy halts shuttle flights entirely, casting a long shadow over the program, assembly slowing dramatically as the station relies on smaller Russian vehicles alone. 2005 through 2006. Shuttle flights gradually resume, assembly missions restarting in earnest, engineers and astronauts working to make up lost time, while incorporating new safety procedures born from tragedy. February 2008. Europe's Columbus laboratory arrives, expanding the station's scientific capability further. 2008 through 2009. Japan's Kibo laboratory arrives across 3 separate launches, the largest single addition in the station's entire assembly history. 2010. The Cupola observation module arrives, giving the crew, for the first time, a dedicated space simply to watch the Earth turn beneath them. 2011. The Space Shuttle program concludes, its essential role in the station's construction complete, the station having reached its full planned configuration. 2011 to today, continuous operation, continuous science, continuous international cooperation, continuous human presence, orbit after orbit, 16 sunrises and 16 sunsets every single day, for more than a decade since assembly's completion, and more than 2 decades since that first crew arrived in November of 2000. There is a particular kind of comfort in hearing a long, complicated story laid out this simply, this slowly, a reminder that even the most complex achievements are, in the end, simply a long sequence of individual steps taken one at a time, across enough patient years, by enough patient people, working together. Even today, the station holds a handful of small, pleasant curiosities worth sitting with before we begin our closing tonight. The station is so large and orbits at such a specific altitude that it remains visible from the ground with the naked eye, appearing as a brilliant, fast-moving point of light crossing the night sky, often brighter than any star, visible for several minutes at a time during the right conditions. A small, quiet reminder for anyone who happens to look up at just the right moment that human beings are living and working directly overhead. At this very moment, the station requires regular, careful reboosting of its orbit, since it experiences slight atmospheric drag even at its considerable altitude, gradually losing a small amount of height over time unless periodically corrected using onboard thrusters or the propulsion systems of visiting spacecraft. A subtle, ongoing form of maintenance, not unlike the periodic repainting the Eiffel Tower, requires every 7 years, though far less visible and far more quietly essential to the station's continued survival. Astronauts aboard the station experience a phenomenon called space anemia, their bodies producing fewer red blood cells in microgravity, along with measurable bone density loss, requiring rigorous daily exercise regimens to help counteract, using specialized equipment specifically engineered to allow meaningful resistance training in an environment where free weights, quite simply, don't work the way they do on Earth's surface. The station's toilet system, a genuinely sophisticated piece of engineering in its own right, uses carefully directed airflow rather than gravity to manage waste in microgravity, recycling a remarkable percentage of the station's water, including, notably, moisture recovered from the crew's own breath and perspiration. And detail that often surprises first-time listeners, but represents an absolutely essential piece of engineering for any long-term human presence in an environment where every single resource must either be carried up from Earth at enormous expense or carefully, continuously recycled. And perhaps most remarkably of all, despite being built from pieces constructed independently across facilities in Russia, the United States, Europe, Japan, and Canada, teams that, in many cases, never once physically visited each other's factories during construction. Every single docking, every single connection, every single interface between these independently built modules has functioned successfully, holding pressure, holding structure, holding an unbroken human presence in orbit for more than 2 decades now, without a single catastrophic assembly failure. A few smaller curiosities are worth mentioning too, before we move toward tonight's closing reflection. The station's name itself, chosen deliberately during those early 1990s negotiations, was the subject of genuine debate among the partner nations. With various alternative names considered before International Space Station was settled upon, a name perhaps lacking in poetry compared to Zarya's Dawn or Zvezda's Star, but chosen precisely because its plain, functional honesty matched the plain, functional spirit of the cooperative project it described. The station's total mass, once fully assembled, exceeds 400 metric tons, heavier than a large commercial airliner, distributed across a structure large enough that, from wingtip to wingtip, along its solar arrays, it approaches the length of an entire American football field, including the end zones. Astronauts aboard the station orbit at a speed of approximately 17,500 miles per hour, meaning the station circles the entire Earth in roughly 92 minutes, fast enough that, standing at a single point on Earth's surface, you could watch the station rise above one horizon and set below the opposite horizon in less time than it takes to watch a single feature film. Time itself works a little differently for the station's occupants too, though the difference is vanishingly small, due to the effects of traveling at such considerable orbital speed. Astronauts aboard the station actually age very slightly slower than people on Earth's surface, a genuine, measurable, if tiny, application of Einstein's theory of relativity, amounting to a difference of only a fraction of a second across an entire 6-month mission, far too small to notice personally, but large enough for physicists to measure and confirm with precise atomic clocks. The station has hosted a small but genuinely memorable list of unusual visitors and objects over the years. A handful of paying private citizens, who traveled to the station as some of the earliest space tourists. Various pieces of memorabilia and cultural artifacts sent up for brief visits before returning to Earth, and even, on occasion, small amounts of specially prepared food and drink sent up specifically to celebrate a particular partner nation's cultural traditions or historic achievements. If you've joined us for our previous 2 episodes, The Pyramid and the Eiffel Tower, tonight's story offers a particularly striking final comparison, closing out a pattern worth sitting with quietly before we finally rest. The pyramid was built by tens of thousands of workers over 20 years, using tools essentially unchanged from the moment construction began, motivated by deep religious conviction, intended to last for eternity. Built entirely by hand, entirely on solid ground. The Eiffel Tower was built by a few hundred workers over roughly 2 years, using cutting-edge industrial tools genuinely new to its era, motivated by national pride and a tight international deadline, intended to last only 20 years. Built entirely by hand, still entirely on solid ground, though reaching higher into the sky than any structure before it. The International Space Station was built by thousands of engineers and hundreds of astronauts across more than a decade, using tools and techniques invented specifically for an environment no previous builder in human history had ever needed to consider, motivated by former rivals choosing cooperation over competition, intended to operate for decades, assembled entirely by hand and by robotic arm, entirely without solid ground at all. Each structure, in its own way, represents the absolute limit of what its era's engineering and cooperation could achieve. Each required its builders to solve problems no one had ever needed to solve before. Wind resistance calculated without computers, 4 independently surveyed foundations converging perfectly above a Parisian park, or modules built on opposite sides of the planet, in different languages, under different governments, docking together successfully on the very first attempt, 500 kilometers above the Earth, and each, in its own way, quietly outlasted the doubt, rivalry, or uncertainty that once surrounded its beginning. The pyramid outlasted the empires that built it. The tower outlasted the critics who tried to prevent it. The station outlasted the very Cold War rivalry that first inspired its 2 separate, competing designs, transforming that old rivalry patiently, piece by piece, launch by launch, into quiet, continuous, orbiting cooperation. There's a gentle thought worth carrying with you into sleep tonight, drawn from all 3 of these stories, stretched across 4,500 years of human building. Whatever divides us, down here on the ground has a way of looking a little smaller, a little more solvable. Once you gain enough distance, enough patience, and enough shared, careful, cooperative effort. Sometimes that distance is measured in centuries, and sometimes it's measured in 250 miles straight up. And so, slowly, very slowly, our station is complete. Every module tested, every interface checked, and checked again across 5 different space agencies, in 4 different languages. Every spacewalk completed safely, hour after careful hour, hand over hand along quiet metal railings, Earth turning silently below. Every doubt, every rivalry, every setback, eventually met with patient, careful, cooperative persistence. If you're still awake, that's all right. There's no need to follow the story any further tonight. There's nothing left to build, nothing left to launch, or dock, or bolt into place. Just let it rest now. The way the station itself never quite rests, but simply, steadily continues, circling the Earth once every 90 minutes, forever falling gently around the planet, and never once landing. Somewhere, right now, 250 miles above, wherever you happen to be lying comfortably tonight, the International Space Station is quietly crossing into another sunrise, or another sunset, its solar arrays catching brilliant light against the black stillness of space. Somewhere inside, an astronaut may be finishing their own day's work, floating gently in their sleeping quarters, watching, perhaps, through a small window as an entire ocean drifts silently past below. Somewhere in Russia, in America, in Germany, in Japan, in Canada. The engineers who once built each separate piece of this station have long since moved on to other projects, other quiet ordinary lives, most of them never once seeing, in person, the completed structure their careful, patient work eventually became part of. Somewhere in a control room, quiet even during the busiest shifts, a flight director, much like the one we visited earlier tonight, is watching a screen full of steady, familiar numbers, everything nominal, everything calm, the way it almost always is, on an almost entirely ordinary night like this one. Somewhere aboard, in the cupola's quiet cluster of windows, a crew member may be pausing just for a moment between one task and the next, simply to watch a slow, silent lightning storm flicker across a dark ocean far below, saying nothing, needing to say nothing, simply watching. Nothing to build tonight, nothing to launch, nothing to bolt into place. Just stillness, just orbit, just time, moving quietly, patiently, the way it always has, over oceans, over continents, over a station that has never once, in over 2 decades, gone dark. Let your breathing slow, the way the station drifts steadily through each quiet 90-minute circle around the Earth. Let your body settle, the way a spacewalking astronaut settles gently into their foot restraints, finally still, finally secure. Let your thoughts drift quietly away, the way sunlight drifts silently across solar arrays, orbit after orbit, with nowhere urgent left to be. Think, if you'd like, of the pyramid, still standing quietly in its desert, 4,500 years old, sand shifting gently at its base. Think of the tower, still standing quietly above Paris, its iron lattice catching faint moonlight, swaying almost imperceptibly in a gentle night breeze. And think of the station, neither standing nor still at all, but moving, always moving, gently circling the both of them, and all of us, 16 times a day, every single day, without pause, without rest, without ever once landing. 3 structures, 3 eras, 3 very different ideas about what it means to build something that lasts. And all 3, tonight, quietly continuing to exist, exactly as their builders left them, asking nothing more of the world than to be allowed to remain standing or orbiting a little longer. Somewhere above you, right now, human beings are sleeping too, circling the planet in the quiet dark, falling gently around the Earth forever and never landing. You can rest the same way, quietly, steadily, held gently the way the station is held in its orbit, by nothing more than patient, careful momentum and the simple, quiet persistence of continuing gently forward. There is nothing left to hold up tonight except your own tired, comfortable body. Nothing left to calculate, nothing left to build. Just this quiet moment and the next one and the next, drifting gently one into the other, the way a station drifts quietly from one sunrise into the next, forever, patiently, softly, around and around and around. Rest now. This has been Sleepy Construction. Good night.